Okay, let's start. Do you have any questions? All right, so let's continue with American options. So we have several features, right? We have, well, we have the stock model, but it's always Black-Scholes, so we don't even need to write it. But again, right? The model will heavily influence how we look at the pricing, but that's more advanced in this course. You have a payoff function, right? Which again can be more general than put or call, but we just do put and call, to start with. And then we have a time horizon, right? Now, this is kind of strange, but only here, right? Just to make things easy, okay? And you'll see, basically, there's a reason why when we explain why like perpetual option makes it easy for us to analyze. Anyway, right, then the price, right, at time t, right, before the expiration, of course, will be the sup or the max of all stopping times, right? Like basically the payoff function, right? On the stock evaluated at that time, discounted back, and then take the average under risk neutral. All right. So now, one thing, right, we want to say is this, right, represents the price of the option, basically starting fresh, right? Starting fresh at time little t, meaning that, compared to V0, right, which is again, right, sup, blah, blah, blah. And then this is just expectation, right? And then of course, you can just, basically you define a stochastic process, right? Starting at time 0 and moving on to time big T, right? Using this definition. The one thing you want to pay attention to is these guys are connected, right? But financially, they may or may not talk about the same object. The reason is, right, it could very much be that the option that starts at time 0, right, by the time little t has already been exercised. Meaning, right, obviously, if the option has been exercised, then it's no longer alive, right? It's no longer exists. It's no longer existing. So therefore, right, these may not be the same option, but the same guy, right? But nevertheless, right, it makes sense for us to discuss a time value, a value process, right? Denote index by time like this. Okay. Again, contemplate on this point. Okay. So this is again, right? If not exercised, okay, before LT. So now, the one thing that is kind of the most crucial thing for us, right? Key results. There are two key results. I mean, there's the call option part, but we discussed it too many times already. So, and that's not key, right? That's just a nifty thing you should should keep in mind. The first one, right, is that the discounted, right, option price is a super martingale, right? Second, if we denote tau, right? And this got to be a little bit tricky like this, right? It depends on where you look at too. So, I mean, so this is with respect to time 0, okay? If you let tau be the first time that the option, right, is equal to the payoff function, right? so here, right, this is exactly where it's respect to time 0. Then, right, V is a martingale, right, on 0 to tau. Okay. So obviously, right, so okay, so let's discuss these two key points, right, and they're more or less the most subtle parts about the American option. So the first part we'll look at later. I mean, we just want to clarify, first of all, what does 2 mean even? So first of all, notice, right, that, I mean, there's the trivial result that VT, right, is bigger or equal to phi ST, right, at any time. Because the option price, right, can never be less than, right, the exercise value, because you can always exercise at that point, right, and get that value, right, according to the definition. So that what that means, right, with respect to time 0. So what that means is, first of all, right, V0 is bigger or equal to phi of S0, right? So you would start out, right, above the payoff, right? You would start out above the payoff. So during this time horizon, right, during this time horizon, what you should have is strict inequality, right? And then if you want, open parenthesis, because of course, right, at time tau by definition is equal. But before time tau, this is strictly, right, greater. So that's kind of how you want to think about it. Basically, right, when the option price is above, right, the exercise value, when the option value is above the exercise value, then you remain a martingale, all right? Another thing is this, right, that this is with respect to time 0. What do we mean by this? What we mean is, right, again, all these definitions still, you know, remain valid. What we mean is that if you say pick up from here, right, because again, actually, right, what this would turn out to be, right, this will be the optimal exercise time for V0, right? So in terms of 2, right, tau is the optimal, right, exercise time. Right, for V0, or, you know, specifically there, meaning that V0 will be equal to this. Okay, like this. Okay, if this is the, or sorry, I guess phi of S tau, right? Because, but it's the same, right? Which is equal to. So notice that, right? No longer soup, because basically we identify, sorry, here, right? No longer soup, we identify which one it is that makes it happen, right? So maybe let me just even do it more. So let's call it tau star, all right? Because to distinguish with all the generic stopping time that we looked at, right? Tau star, tau star, tau star, tau star, okay? Like that, okay, tau star. So what I mean is this, right? That is the optimal exercise time for V0, but pay attention, it may not be the optimal exercise time for VT. If you want, right, VT, because again, right, VT is like you start fresh, you kind of forget the past, right? Then if you want to find the optimal exercise time for VT, then you use this definition, but starting at T, you understand? So, right, so this is like a moving definition, right? Here is the optimal time for V0. Again, right, that's the subtle thing. Still keep in mind all this definition, but if you want to find the optimal exercise time for VT, then you will need to start at time T forward, okay? Like this. And the question about the way it's written, right? We'll explain the results later. All good? All right. So let us, right, look at the reasoning for these, right? So reasons is, you know, it may or may not be super rigorous, but at least try to give some, ideas behind this, right? So there are two ways to approach this. And first, right, and the one that I like you guys to kind of think more about is the financial intuition, right? And the financial intuition, right, is again about a trade-off, right, between one share in the future and one share at the present, right? So again, right, the idea is if someone asks you to take like one share of, I don't know, Google stock, I don't know, right, the VIX index, gold, whatever, right, compared to one share of that right now, right? How do you feel about this, right? Again, it's an exchange, all right? So in other words, in between, you cannot do anything, right? You either have it now and wait to your future before you can take any action, or wait to your future and take that. So the point is, right, that if you are indifferent, then that means that the discounted price process of that thing must be a martingale. Okay? But if you have a preference, then that would not be, right, a martingale. And again, the direction of the preference, right, will tell you whether, it's super, sub, or even something even, more weird. And so, right, let's review that again, right? I think this thing you have to really think out loud, but for a stock, right, and that kind of thing, you would be indifferent, right, between the trade-off, right, VT and V0, all right? And actually for that matter, for European options, it's the same thing, right? Because basically, you cannot do anything, right? You cannot do anything between time 0 and time little t, right? As long as it's before big T, right? You just basically the value just move by itself, and you just kind of trade off between this same, basically essentially the same object. You can also throw in the exotic option in this bunch too, right? The only point though is you have to be careful to phrase it, because there might be some history in the past you have to watch out for, right? Like it's knocked in, knocked out, that kind of thing. But so far basically nothing really that we looked at changes anything like this. Again, mostly because there's nothing you could have done right between these two time point. Well, you either buy it at this point or buy it at that point, right? It's the same thing. On the other hand, right, with the American option, right, then it's clear that you want to hold one share of the American option, right, at time 0 rather than at a later time, right? Again, the reason is very simple, right? Because you by entering the action early, you could have taken some action right before time little t, right? So the window, right, the actions more, right, opportunities, right? To optimize, right? On 0t, right? Versus tt, right? So it's a very, very simple intuition. And if you have this preference, then that clearly means that the inequality must point in this way. And in general, right, you can you can put any time s less than t, right, and the same argument would apply, right, and that would exactly establish the super martingale, right, property in general. Okay. Any question? All right. Now, so that's point one, right? That's the financial intuition for point one. What about point two? The point two actually still goes back to point one, but now sharpened, right? The intuition a little bit, like this, right? Again, basically, it's still V0 and VT, right? And again, notice that, right? The point is this: it's his time 0, his time t, right? You are comparing the value of the option at time V0 and the value of the option at VT. Keep in mind that by VT, right? What we mean is you enter the option at time t, right? And having the time windows like this, right? Not knowing what has happened in the past. Or basically, this is just a fresh option, right? So that's a confusing part. This and this guy, just for convenience sake, think of this as two different objects, if you will, right? It's not, doesn't have to be the same option even, right? On the other hand, right? Suppose that there's a Tweety bird, right? Some guy with a crystal ball, right? Who tells you that, hey, look, right? Let me tell you what. For anyone, right? For the guy who started earlier than you, right? Let me tell you that by your time, he would not have exercised the option yet. All right. Someone told you that. All right. Which is kind of strange, right? In terms of knowledge, but let's just assume that for now. When you enter the market, someone told you that, right? Someone tells you that, well, right? The guy who started earlier than you, guess what? He didn't even exercise yet. So from your point of view, what do you think? Hey, I didn't lose out on anything, right? I did not lose out on anything because the guy who started earlier than me has not even taken his opportunities. So from that point of view, me and him are actually equal or indifferent. Does that make sense? And that goes for actually, right? If the guy who started here didn't exercise early, then any guy in between, right, cannot exercise early either because their window of opportunities is actually less than this guy, etc., right? What this means is, right, V0 and VT are indifferent here. Because, right, the opportunity to exercise lies in the future. Okay, so both you and him are exposed to the same kind of windows. Therefore, right, and that explains the martingale, right? That explains the martingale property. Any question about this? All right. Again, I urge you to contemplate this intuition and make sure that you're either convinced by it or you are not convinced, and why you're not convinced, and you want to think about that. Now, I want to also try to establish some mathematical intuition for this a little bit, because after all, right, I mean, we should try to look at the same thing as many ways as possible. And as I pointed out last time, right, the mathematical intuition is not quite straightforward because of the soup, right? This soup right here is a rather not easy operation to work with because, basically, right, when you cannot pass it outside or inside expectation, that kind of thing. So the point is, right, with that, the mathematical definition, how do you establish that? Let's just take, right, 0t, right? How do you establish that this is true using VT as a soup definition and V0 as a soup definition, right? Well, the key is this, right? We will not prove it super rigorously, but we will prove it, right, assuming that tau star exists, all right? So for now, let me just do this. Tau star 0 and tau star t exists, all right? Which again, right, I convince you that it does, right? They do, because again, right, it's basically this guy right here, right? The first time that you meet your exercise value. Oh, by the way, right, I'm a little bit lazy in this course, but basically everything we do has this, flavor, right? If it never happens, then it must be at the terminal time, right? It cannot go on forever, all right? So when we define the time, if it doesn't happen, that means it will be terminal time, right? So suppose that these two optimal time exist. What does that mean? That means that V0 is exactly tau star 0 phi of S tau star 0. And Vt is expectation of eta minus R tau star T minus little t phi of S tau star T, right? Condition on Ft, right? All right, so basically, these are the time, right, after 0 and after little t that exactly hit the American value, all right? So if we can assume this exists, and you see why this is good. If we assume they exist, then the soup disappears, the soup disappears. So let's see how this works, right? When you take this expectation, right, when you take this expectation on the right-hand side, then basically, right, plug in the optimal definition. Then you would get e to the minus R tau star T, right? And then you have this. All right. So do you see? Basically, you still have the conditional expectation inside, and then you bring out, right, the discounting outside, and it just be the single discounting. And now you're here, right? Because we no longer have the soup, right? We just have this. Then you can invoke that iteration properties, right, of conditional expectation of conditional expectation is just expectation. So in fact, here you got this. All right. So basically, right, again, assuming an optimal exercise time exists, allow you to bypass the soup here, and that in turn allows you to, right, canceling out you combine the two expectation into one single expectation. And right here, what do you know? Well, this is exactly, right, an expression like the one in the definition of V0, right? It's just exactly one of those stopping time that takes place in 0t. And V0 is the max among these guys. So this cannot be any more than V0. And there you have it, right? So notice, right, that this is actually just a fancy way to write down the intuition, right? Because all we say is if you optimize over here, it must be one of the time that you can use in the past, right? That's exactly the mathematical intuition. Is just writing down in symbols what we wrote down in here in English. Okay. Any question? Okay, so far? Now, the second one I want to say, right, is something a little bit more subtle, and it helps with the intuition, but yeah, so let me write down, right? So we know, right, from one that is a super martingale, right? We will establish the martingale part later, up to tau. But the second one actually will be something like this. Even though V is a super martingale, V is the smallest super martingale dominating the payoff function. By the way, right, the word dominating here, you don't have to worry about it. It's the mathematicians' fancy word to say greater than or equal to at every point. All right. So what does this mean? What it means is, suppose you come up with some other arbitrary, all right, super martingale, let's say called X, okay? So let xt be another super martingale, right? Meaning it has to have super martingale property. Whoops. And it must be dominating the payoff function because, right, everything here must be above the payoff function. Then what 2 says is your guaranteed VT is no more than it. So we'll show this, all right? We'll show this and we'll try to show you what the consequence of this is. But first of all, right, let's just try to contemplate what this means. So this actually, right, the word here, the keyword here is smallest. And it points to also something optimal going on, all right? Something optimal going on. And of course, right, no doubt, it's connected to the soup, right, part here, right? The soup part here. Soup means the smallest upper bound, right? So there's the connection. But let's just look at from, a financial point of view or from a modeling point of view. What this says, right, is first of all, remember VT is a price process, right? VT is a price process. Again, right, I would say anyone who thinks about this a little bit would clearly, right, know that VT is bigger than or equal to phi ST. There's nothing, right, that you can deny about that. Also think about a little bit, right, whether you use this fancy argument or you use this, a little bit more mundane argument like this, you would also conclude it's a super martingale, right? So that's easy. This part is a little subtle, but what it says is if you can get to this, what it says is this is like the smallest price, right? You think about it, right? American option, right, is a price process that dominates the payoff function. But it cannot be too expensive. That's what they're trying to say, right? You cannot, just because you dominate this guy, you cannot be as big as you want, right? That's what you would hope to have a very expensive, right, an option on your hand. No, right? That's not true. You can do all these things, but you have to do it in the most optimal way possible. You cannot waste any opportunities, right? So that's what it says. Another one you can think of is like, there's something corresponding to this in physics where it's hard to describe, but think about like you have some, let's say some stick or something like that, in 3D, all right. And let's suppose that you let some cloth or something like that, right, fall on this, all right. So the cloth will be pulled down, right, by gravitation. However, right, at the height, right, the height of the cloth will be dominating, right, the stick. So the stick here is like the boundary that it cannot cross, yes? But the cloth will be higher than the sticks in an optimal way, right? It will not waste any height in other parts that is not controlled by the stick, you know what I mean? So anyway, right, this is kind of an obstacle description that also has some analogy in physics, all right, in nature. Basically, you have to do things in a very economical way. All right, so how do we establish this? The way to establish this is actually surprisingly easy. Well, so the argument, right? Let's try to show this at time 0 because anything else, right, is similar. Okay. So, well, what do you know, right? So what you know, right, is that V0. So hold on, let me see here. So let's look at X0, right? X0 because it's a hold on. Let us take a look at expectation of e to minus RT st, right? Phi of st, let's say. All right. Okay. So let's look at this expression. First of all, right? This guy is dominated, right, by xt. So it must be less than or equal to e to minus rt v of xt. Sorry, xt, right? Agree? That's by domination, right? The x is another martingale that dominates this. On the other hand, by super martingale, this is less than or equal to x0. Agree? So I will just write down the inequality by the assumption. All right. So this is just by assumption on the x. But pay attention, right? Actually, I could change it to any stopping time, right? And they will still be the same. So I can change it to stopping time, and all this would still be the same. But then, right, this is where the mathematician pull out their, trick. What does this say? This says that x0 right here is an upper bound, right, for any expression of any expression of this type. Any expression of this type will be upper bounded by x0. V0, right, is the sup of this guy, meaning it's the smallest upper bound. A smallest upper bound can be no more than another bound. Therefore, V0 being the sup of all this expression will be no more than this. Okay. Any question? So, right, even though the price is a super martingale, it cannot be too high. All right, it must be just high enough to be a super martingale, no more than that. All right. So let's try to, any question? Let's try to see, right, the intuition for this, how this plays out. And for this, right, let us look at just a deterministic picture, all right, but it will help. So let's say this is time, right, and I have some, arbitrary function, right? Let's call this phi of st, all right. Again, this is, a deterministic picture, so it doesn't have to be like this. The key difference, if you want to ask, is that here I would give you the intuition point by point, while, right, the language would try to prove is on average, but it will kind of have a similar taste. So let's see, right? Basically, we want to find out how the VT looks like, right? Using our description. So first of all, right, we show that it's a super martingale, right? So in the deterministic language, right, a super martingale means a decreasing function, right? A super martingale in the deterministic language is a decreasing function. So imagine, right, that you try to draw a decreasing function, and this decreasing function must be always above this guy, right? So that's what we got so far. We want a decreasing function that's always above this guy. But that's not all, right? That's not all, right? Because you see, if you just want to draw any good or decreasing function above this guy, then there are tons of ways for you to draw that, right? I mean, there's a million ways. This right here actually gives you a way to narrow that down. Why, right? Because number 2 says you cannot be arbitrary, right? Because you must be the smallest one that does this kind of thing. Okay, you must be the smallest one that does this kind of thing. So you think about it, right? How would you be the smallest one that dominates the phi? Try to think about that a little bit, right? A smallest decreasing or smallest non-equal. So here's a challenge, right? Draw or really, right, is our smallest, but the smallest non-decreasing function dominating. All right, try it. Think about it. So actually, maybe let me drop this part, right? And let me just make it easy and let's do this. Right, let me just make that. All right, this is phi. All right, and let's suppose t is somewhere here. Right, draw the smallest non-decreasing function dominating phi. Think about it. All right, have you thought about it? Okay, so last chance. Here's the answer. This will be the smallest dominating, the non-increasing, sorry, right? Non-increasing, not non-decreasing, non-increasing, right? Okay. So you see, what do we got? Basically, right? You must be dominating this guy. So for certain parts, right? The dominating would be only a horizontal line because that's the smallest way you can do that, right? If you go any lower, then you'll be increasing, which is not non-increasing. But if you are above that, you can always pull it down to horizontal. For the part of the function where it's decreasing, then you can just follow that. So what does that mean? This is exactly the part where we say when Vt is bigger than Vst is a martingale. A martingale is a horizontal function. So, right, this optimal, you see this optimal part, right, the smallest part actually nails it down completely, right? You cannot draw an arbitrary function anymore, right? You have to draw the tightest cover, right? Non-increasing cover for this phi. And there's only one way to do that. Okay, again, a bit abstract, but of course, this is, I did tell you this is a mathematical argument, right? But this is exactly another reason to see why, right? That that we have those martingale characterizations. Any question? All right, now let us look at the optimal exercise time. All right, of course from 0, right? So remember, right, we say V0 is the sup or the max, right, of all tau of discounted payoff. And then we say, right, if we let this to be the, oh, sorry, right? So actually here, it assumes that you know what Vt is, right? So I think I should let Vt, right? Define Vt actually. Because here it assumes that you know what Vt is. So tau minus t, right? Condition of Ft. Right, so this also defines V0. And then you let tau is the first time starting at 0. That this price process is equal to phi of St, right? Tau star. And if you define like this, then V0, right, will be discounted. Right? So again, right, I want to go over this and try to argue it out. At least it makes sense. So what do we want, right? So here's some thought here's some thought experiment, right? Again, you want to make the simplest case possible to give you some intuition. And even though it might sound silly, but it might be very enlightening. For example, right, let's say at t equal to 0, right? What if v0 equals to phi of s0? What do we do? Right, just take the most objective, standpoint. Right, we know, right, that v0 must be greater equal to phi s0, right? But suppose, right, you have the American option, someone hands it to you, and suppose you check and you're like, oops, it's exactly the exercise price. What do? Do you continue to hold, or do you exercise, and why? Right? Now think about it. Put yourself into the position of the American option holder, right? Someone just hand you the option, and then you check, and somehow it's exactly equal to the exercise value. But right, you don't have to exercise right now. You can wait. Okay, so what do you do, and why? Anyone? So, right, again, I hope, right, you see that is, so this kind of easy question test your intuition on American option, right? You must understand your way out of your way to argue about American option to answer this even, I guess, right, simple question. Again, right, the knee-jerk answer, and the correct answer must be exercise, right? I hope no one would entertain this as the right answer. But of course, right, the word why, right, is the question, right? Why do you say that? Okay. And so you see, right, the key to the American option game is the exercise clause. Meaning, right, if you are having an American option, the only time you can exit the option early is via exercise term. There's no other way out. Okay, so that's one thing you want to think about financially. When you hold an American option, you either hold it, or if you want to exit, you can only exit with the exercise value. Now, right, what this means is at time 0, right, this is your first window to exit the option if you want. Now, do you want to exit the option or not? Well, the answer is, right, it's unclear, right? Because I'm sure what's going on in your mind is this: what if the option goes up, right? That's what everyone would think about, right? What if it goes up? Why do I have to exercise now, right? So how do you answer this question? Well, again, right, this shows you again that you have to connect what you learn to what happens in real life. This is always the question that gets asked. But, right, someone will say something. Yes, that's exactly it, right? but VT is a super martingale. All right. So what that means is VT will decrease, right? Or rather E minus RT, right? Because you have to discount it 2 times 0 on average. All right. And therefore, right, let me tell you the formal argument, and I'll explain some peculiarity here. That, right, the formal argument would be that right now you have an opportunity to exit at this value, which is equal to the option value. You know that if you wait, right, is this may sound a little bit like, depressing, but think about life. Life can only go downhill from this point on. Trust me on this. You only get old from this point on. So therefore, right, either have fun now or you're gonna just suffer more in the future. So therefore, right, if you know this is the case, then might as well just exit. Okay, sounds like a very fun way to think about life, but that's what it's trying to say here. Now, right, one thing that, so any questions so far? So one thing that might be a hiccup to you is on average, right? And that's it. So that actually does allow for the fact that V as a process can pick up in value. Absolutely. Okay. Like, if you plot V, right, there's no denying that it will look like this. So in other words, at some point in the future, it will go up in price. However, right, there are two things about this, right? Notice that this argument would also apply to stock and that kind of thing, right? Notice that with stock, it can also go up in value. So why are you indifferent between S0 and ST to begin with, right? You have to be very clear about this. Like I said, it sounds like an easy thing to accept, but it's subtle because it goes against some intuition in reality, right? So to answer your question, here's V0, right? And if you try to simulate VT, definitely something like this will look like, will happen. So you can quote that, well, what if this is the case? Then would I be silly to exercise right now? Right? So the answer is, first of all, right, this is not discounted back yet, right? But that might be mild because R might be close to 0. The more serious thing is, this is just one of the many paths that we can take. We can take another path like this, and another path like this, etc. Right? The point is you do not know which path it will take. And the math tells you that on average, it will be lower than what you're having right now. And that's the best clue you can take. All right. And don't forget one more thing is we're in the risk neutral framework. So we're not being risky about anything at all here. We don't have any risk preference. If someone has a risk preference, they might choose to continue. I would agree on that because they are risky. They want to take more action. But so, right, all these things, I'm just trying to tell you that, right, the exercise decision is correct. This is the right answer to give, but be very clear to yourself on the subtle points on why this is the right reasoning, all right? Any question? All right, so now, right, with this thought experiment, I think, right, then it's clear that the other way holds, right? That if this is true, then we continue, right? I think no one would. Actually, right, I think this is harder, right? This is easier because, right, if you exit, you get less than what you're holding right now, then no one will be crazy enough to do that. Okay. So what that means, right, is clearly, right, clearly that when you look at the optimal exercise time for time 0, the two thought experiments that we just do shows us that tau star can no longer, so right, tau star must be at least the first time that V equal to phi. Do you understand? right? Because, so what I'm trying to say is the two-thought experiment we looked at right here shows you that you definitely do not want to exercise, right? So what we are saying, right, is if you should start out above this, because if you don't, you already exercise right away, and this will hold. This is true. Oh, sorry, this is true, right? But if you start out above, right, then you will continue to hold, right? Because this argument would work all the time. So you would never exercise before that time. So that's easy, right? That's easy. I guess the kicker is this. Why would it not be strictly greater? In other words, right? You guys should have, I think no one would be surprised if you have taken something on American option that, right? They tell you something like this, right? If you do this and you do this, right? So this is V, right? And this is P, right? Here's where you exercise, right? So again, it's clear that while you're above, you definitely don't. But let me ask, right? Why not go past this point? Why not go past this point? Right? Why? So, right, suppose you're an American option holder. You keep track of the option value, right? You got the hit. Why not go past this point? Why at this point, then an alarm goes up and say, you got to exercise right here. Why not go beyond this point? Well, the reason is exactly this thought experiment, right? Because, right, because exactly, right? You know, this argument, right? And the value can only decrease in general from then on. And you have an opportunity to exit at that price, so you better take the chance. So that's it, right? That's the key. Okay, so again, I want to explain, right, that somehow this is actually very intuitive and it's not that mysterious, if you want to think about it. Any question? Okay. Now, the last thing I want to say, right, is 3, right, is not useful, or actually that's a polite way to say it's completely useless in option price evaluation. Okay, and I hope it's clear to you why. So imagine yourself, right, and I think in the homework of this week, you have some taste of that. Suppose that you want to chase what this tau star is, right, in the hope of using the tau star to simulate V0, right? You will never get that to begin with. Why? Because tau star assume that you know V to begin with. So why would you, right? I mean, why would you, right, find V0 if you already know V, right? So in other words, this is a sort of like a bootstrap kind of argument in the sense that, right, to find tau star, you better know V, all right? So it's fine, right? It's fine as a definition of stopping time. It's fine as arguing out if you have these value processes, then these guys must be connected like this. It's perfectly fine. But when at the end of the day, if your goal is to find out what VT is, then the tau star above is useless. Okay. On the other hand, actually what's useful, even though more abstract, is exactly this guy right here. Because you see, right, this guy, even though it's abstract, it requires nothing that is bootstrapping, right? It's hard. You have to find the smallest one that somehow, dominates the payoff function, but it's clearly defined, right? It's independent of anything else that you need to know. So in fact, right, I hope, so the point is this, right? The martingale characterization, right, is the useful way, right? Okay. So pay attention to that. It may be very mysterious to people that this might allow you to simulate V0 very easily, except that unfortunately no, right? That is a circular argument in terms of simulation. All right, so now having said this, right, now we can go to the PD, right? So for the PD, we have argued, right, and I will stop, I will not repeat it, that there is some function, right, depending on T and ST, such that the value of the American option is equal to that function. Okay. So the discounted, right, option price is a super martingale because, right, is equal to this. Therefore, again, right, we'll skip the whole Ito's formula, but I think you've seen it enough by now to know that we just do RS, right? Okay, so that's the first one. The second one, right, is exactly about this picture, right? And this is very helpful. As long as you stay above the payment, the payoff function, then you stay horizontal. So in other words, this is 0, right, for VTX greater than or equal to phi of x. Sorry, not greater than or equal to, right? That's wrong. Strictly greater. All right. And finally, right, you require this. So notice, right, we need all three, right? We need all three to describe this so-called PDE. And this is called the obstacle PD, all right, which is a big area in that literature. So you don't have to worry too much about it, but exactly is describing what I was trying to say above, that you have an obstacle, right, which is this guy, whatever it is. The target function must stay above it. That's the obstacle, but it must stay above it in a minimal way, in the sense that if it's strictly above the obstacle, then it must be very flat. And where is it allowed not to be flat or decreasing? Where it's kind of equal to phi. That's where it has no control, right? Where it's equal to phi, then it just follow phi. And so actually where phi is decreasing, then it'll go like this, right? But where phi is increasing, then it must stay above it in a flat way. All right. Finally, here's a fancy way to combine these three conditions. I'm not a big fan of it, but somehow you will see this. So I just want to write down. It's also in the note. So first of all, notice that I negate the expression on the left. And then do this. All right. So again, math people like to be clever, right? They like to pour a lot of expressions into one compact way and say, haha, look at me, I'm smart. But the point is this, don't be too bothered about it, right? What does it mean? What they say, right, is the minimum, right, of two expressions is 0. That means that one of them must be 0 and the other one must be positive, right? That's all. That's the way to say that dichotomy, right? One of them must be 0, the other one must be positive. Well, so let's check, right? When this is 0, right, then this guy must be positive or non-negative, right? So that's exactly that, right? Because if v is equal to phi, then this can be non-negative. But when this is equal to 0, then this must be, right, positive to, for that, sorry. So here, if this is positive, right, then this must be 0 because the minimum is 0. On the other hand, right, this guy must be non-equal to 0, so it's negative. You check, right? Basically, it's just equivalent. All right. But the thing is, though, right, you got to give him credit for this, because if you do this, then it's clearly an equation, right? An equation. The way I wrote it over here, right, it's not clear that it's an equation, right? PDE. But if you do it like this, right, it's clear that it's an equation, but it's a highly non-linear, right, equation in terms of V. So that's what it is. All right. I prefer this. It's more intuitive. You just know what you're talking about. But anyway, any question? All right. Now, so just some quick words about this guy, right? Obviously, you have no hope to solve for this analytically, right? No formula here. Even the numerical procedure for this one is highly interesting, I think. I believe that Professor Larson's class, computational finance, used to assign this one as a final project, I think. So yeah, so it's that hard, right? So I definitely don't know much about this. So, but I just know it's very, very challenging. So we just stay like this, right? And wash our hands off of it. But there is numerical solution, all right? By putting question mark here, that doesn't mean that it doesn't exist. I know it exists. I'm just saying it's quite challenging to code that up, right? And it has a lot of literature. All right, now for us, what we want to do is to look at a easier version of this. And what's the easier version of this? Perpetual option. So first of all, let me explain what it is about perpetual option that makes it easy. So first of all, perpetual option means t equals to infinity. Now, when time is infinite, right? And also, this is also because of Black-Scholes, okay? Highly dependent on Black-Scholes. Black-Scholes is time homogeneous. What does that mean? What that means is, right, look at the way the stock moves. dst is rst dt plus sigma st dwt, right? Like this. Suppose that, this is the model, and of course, suppose that it holds for 1,000 years. Of course, that's not true. And you see already it's kind of weird. But, right, suppose that, 1,000 years from now, suppose Google is still around, then Google stock will still move like this. Then, right, someone from looking at Google 1,000 years from now will have no difference from the way we're looking at Google now, because interest rate is still the same, volatility is still the same, it still moves in this way. All right, and that's exactly what the time homogeneous is about, right? Technically speaking, this should be the function of t, that kind of thing. But right, so basically, it doesn't matter where you are in time, as long as you're given a time point, the movement will be similar. So if it's time homogeneous, then notice that, right? And here's just an observation to help you. All like Euro type options, and even exotic maybe. I'm not so sure, but I think it's true. Depends on t via t minus t or tau. Right, and this is actually the point that some of you were confused about. Right, this is where the theta, right, the Greek is the derivative with respect to this, while the PD is with respect to this. And that's someone asked, right? And if you look at all the way you code, you'll see that a lot of times only this term shows up. Little t, I don't think ever show up by itself. Right, okay. So again, that's a big statement, but look back. I don't think there's a time that little t show up by itself. Little t only show up like this, okay? So therefore, right, if big T is equal to infinity, what happens? Oh, by the way, right, this is also because it's time homogeneous. So when big T equals to infinity, let me be very quick, right? But I hope you see it's intuitive. Then VTX, right, as a function of the price is no longer is independent of little t. Or that's a way to say that it's only a V of X. You understand? So when we look at perpetual option, the perpetual option value only depends on the stock price, and it doesn't matter where you are in the time process. So that's what I'm trying to say, right? So basically, what it says is, right, if you have no horizon, then whether you're here or whether you're here, as long as the stock price is the same, then the option value is the same. That's all it's trying to say. And I think this is not that hard to accept, right? Because you have no limit on your time horizon. The parameters won't change. It's the same. All right. So, okay. What that means, right, you see, is this PDE here becomes a ODE. So even though it's still an obstacle ODE, but it's much easier to solve because we eliminate one variable. Right, so we still have minus RV plus V sub X RX plus V sub XX. Whoops. 1/2 sigma square X square, right? Negative like this, right? That is equal to 0 if V sub X is bigger than phi of X, right? And V sub X is bigger than phi of X. That's it, right? Notice that the little t, right, disappears. All right. And this can be solved analytically. And I think that's, you already asked to play with this on the homework. So let's explain this a little bit. Any questions so far? All right. So let me try to tell you, right, how the intuition for this works. So notice, right, actually, when you look at this, you have to kind of see what you are looking at, what you're not looking at. So notice that there's no t in here, right? There's no t in this picture, so it's a picture in terms of x. All right, it's a picture in terms of x. Again, X represents the stock price, so it's only positive. Okay. And let's suppose a fee is whatever, right? And exactly now this looks like the above that I draw, right? So suppose this is fee, right? Whatever. Okay. And actually, right, again, it's almost like this picture right here, right? But here I was drawing T, but you know. And then, right, what happens is this. You know that, right? So basically the idea is, if only, right, if only we know where V of X is bigger than V of X. Why? Because, right, suppose it's somewhere here. We know that here it must be strictly bigger. Then what? Then that must mean that there, it must be equal to 0 here. We just have to solve the ODE. Yes? And then that's it. Why? So suppose, right, this is where, so this is, let's say, x1, right, x2, x3, x4, right? Suppose this is where it happens. Then all you have to do is solve it there and solve it there. And what about the rest? The rest is equal, right? Because if it's not bigger, then it must be equal. In other words, then you just connect like this. You understand? So that's mostly, right? So notice this kind of like circular argument still goes into this flavor, right? That again, right? We reduce the ODE to the PD to ODE, right? This is the ODE right here, which can be solved, right? I'll show you later. Now, the point is, right, that if only we know where we need to solve it, then we can solve it. And then the rest is just equal to phi because phi is given. But of course, right, that's a wish because to know this means to know the function, know the solution, right? But again, you know, math people are smart. They have a way to go around this. But you know, that's the idea, right? If you only know this, then you just have to solve the ODE where you need to. All right. All right. So let's see how the math people get around this. Well, they got around this, right? Wish or this argument by guessing, right? And this is where I guess it throws a lot of people off, right? You would think that math doesn't start with guess, but math actually starts with guess a lot. You guess that there is some value such that, okay, sorry. First of all, right, now we specialize to put option, all right? Otherwise, the guess makes no sense. This. Okay. Yeah, definitely. If it's a more complicated fee, then we don't know. But notice, right? This is the put option. Then what happens? What happens is, right, now anyone would know, right, with the put option, you would continue to hold when the stock price is high, right? And you would exercise when the stock price is low enough, because that means you have a payoff that's substantially large, right? With a put option, if you have all the time in the world to wait, right? That's T equals infinity, all right? So this is put option, all right? So let me first of all, then the intuition is hold until stock drops to a low enough level. Okay. By the way, right? So there is this region, right? This phi of x, this v of x bigger than phi of x. right? This obviously is referred to as a continuation region, right? And this region right here is referred to as the exercise region, right? And so combined with our intuition that we hold a stop until it gets to a low enough level, then the continuation region would be equal to stock price is high enough. Sorry, X, right? And the exercise region will be, I guess, maybe strict, right? I don't know where you want it. It doesn't really matter, right? What equality is. You understand? So in terms of picture, right? What we're saying is like this. Here's X, right? Here's K, right? Here's phi of X, right? Now, there will be a level, right? And by the way, this level is not necessarily K, okay? It's not K actually. It will be some level, right? Could be below, could be above, right? Who knows? But let's say it's above, right? For now, I think it's above. Actually, we may also try to see if we can argue it intuitively. But basically, the intuition is, oh, actually, yeah, should this level be below or above K? Yes, right, must be below because, otherwise you get payoff of zero. Why would you do that? So, right, actually that's just, right, L star would be here, right? But we don't know how deep down L star is. So that's what we need to solve. But notice that based on the financial intuition, we have simplified, right, to this. That basically, right, for this region, you will solve the ODE. And you may get something like this. And then for this region, you just simply follow the payoff function. So that will be your solution. Okay. Again, right, it's simply a guess. So this is a guess based on, right, financial intuition. So, but that's what math people also operate on a lot. Basically, you make a guess and you try to solve it. And if your solution makes sense, then you got it right. Who cares? Who cares how you got it? But basically, right, there's no, yeah. So in general, for a generic fee, the continuation region would be very hard to guess. So that's 50% or 80% of the game is to guess what the region looks like. But if it's a very simple thing like this, then, right, it looks pretty simple. No, notice that L star now, right, must be part of the solution, okay? In other words, that doesn't get you out of jail free. You don't know what L star is. But suppose that, so the point is you make a guess that the region looks very simple. Left and right, right? Left is continue, right, left is exercise, right is continue, right? But it simplifies it compared to, right, God knows what. And then you solve your ODE and do some, calibration and check that things work out the way it should. All right. Okay, so that's it for today. All right. On Thursday, we'll continue and finish with this part.
Thank you, Professor.
Yeah. You can just hit log out and I think it'll take care of it. Yes, we will find L star. I mean, L star is part of the solution. We'll find it. It's found by smoothing, basically matching the left and the right part. Make sure the matching is smooth. So that's another condition for you to find L star. Yeah.